Alright, welcome back to Network Information Hiding. Today we will discuss chapter 4, and this is an introduction to the information hiding techniques in the network. So if we look at the following figure from our book, then it shows us different concealment methods in communication networks. One can conceal the identity of communicating parties, that would be anonymity. One can also conceal the content. Cryptographic techniques can do this. However, we want to hide the communication process because we deal with steganographic issues here, and this can be done in two different ways. First of all, one can let the covert transmission blend with the overt transmission. That's network steganography. And the other one is that we destroy the overt transmission, so the actual transmission, by obfuscating the traffic type, which leads to the concealment of the traffic's characteristics. However, we will focus only on network steganography. So our goal is to let the secret traffic blend with the overt transmission. So the covert transmission is hidden in the overt transmission, and we want to hide the existence of the communication. Nobody should notice that there is such a secret communication going on. In the past, and sometimes still, there's no clear distinction between network steganography and network covert channels. So network steganography and network covert channel research was handled separately. And back when I was doing my PhD, this was quite frustrating for me because it led to similar ideas published under different terminology. So this is like a wild forest and of terminology. So we cleaned up the terminology, we unified the understanding of both communities, published in the book that I cited many times already. And a steganographic method creates such a covert channel. That's the definition that we proposed. So there is no network steganography without network covert channels, because these methods, network steganographic methods, create network covert channels. And what we want to have in the end is a network covert channel. Covert data is hidden in the overt network transmissions, and the cover object in network transmissions is the carrier. So the network packets, the frames, the datagrams, however you call it, depending on the layer. And the advantage is a constant transmission in comparison to, for instance, hiding data in one image. You transfer the image and then the transmission is done. But if you want to send more data, you need a new image. Here you just have a continuous flow of data if you want, and this allows permanent data leakage, for instance, which is also resulting in a higher threat in terms of its durability. It's difficult to analyze all network data because network traffic contains so many information that allow to hide hidden data in it, that it's almost impossible to detect and search for all forms of network steganography or network covert channels in such a traffic. Another advantage is the smaller delay, so you can immediately get a reply and you can immediately send data. If you first have to wait for someone to send back an image, then that's taking longer. Of course, one could also send the image over network steganography, but then in the end, you use network as a carrier, at least. With the growth of the internet, options for network information hiding grew, and they still grow a lot. Here's a simple example of a method. We see a trivial covert channel here, that exploits the IP version 4 reserved bit in the IP header to send the message 1001. So the reserved bit, we see here some 4 packets that I sent using the SCAPI tool, which is a Python-based tool where you can easily compile network packets. I assume you know what an IP packet and the source IP and so on is. Anyway, every IP header has some flags. Reserved bit that is just not used, a don't fragment flag, and a more fragment flag for indicating fragmentation information, and also there's some fragment offset. So what we did here is to exploit the functionality of the reserved bit because nobody uses the reserved bit. I set it to 1 or 0 using this hex value. And so I set it to 1 first, then twice to 0, and in the last packet to 1. So this would indicate a hidden bit message 1001 and would be a very simple form of a covert channel. However, it is also a clear anomaly because the reserved bit is usually not set in IP packets, which will lead to a rather easy detection. But this is one of the very simple covert channels one can implement. Another example is ping tunnel. Ping tunnel is a little bit more sophisticated. So the ground setup is as follows. A client wants to communicate with a destination over the internet, but the client is permitted to directly communicate via TCP to the destination. For instance, let's assume the port is blocked by a firewall. Now, what an attacker can do is setting up a proxy server on some reachable web server or wherever, some virtualized host or anywhere in the internet, some server, and pack the TCP information into ICMP, send this to the proxy, and the proxy forwards the packets to the destination. When a reply comes, the destination answers the proxy, and the proxy packs the reply packet into the ICMP packet again and sends it to the client. So in the end, it's as follows. We have our IP packet here with ICMP attached, and what they send here is an ICMP echo reply, I think. And in the echo packets, in the echo reply packet, you have some payload. And in the payload, you pack the hidden data, which you can see here, plus some meta information, like information required for the proxy to see how long is the data packet that is hidden here. Is it an acknowledgement? What's the state? Who's actually communicating? Which IP and port? And so this is a simple version of covert channel internal control protocol. I will discuss such protocols in detail in the chapter on sophisticated hiding methods. So this is a good and working example. Ping tunnel is now even developed further. I think there's a GitHub repository, and we analyzed this protocol and proposed also improvements in this paper. It's open access, so you need no widely access to read it, because there are some things that you can improve and still might be things that can be improved. But if you look for a tool that is good for understanding covert channels, then it's ping tunnel. Also, there are rules available for typical intrusion detection systems like Snort that can help you to detect ping tunnel. So it's still easy detectable because this magic number is always the same. So some tools just search for the magic number that indicates the presence of ping tunnel packets, and that is used to distinguish between ping tunnel and legitimate ICMP echo replies. I will now go through some very fundamental categories of covert channels in the network. So first of all, we talk about network covert channels and not about local covert channels that I already introduced a few chapters ago. like those exploiting CPU load between two processes that want to communicate. But there are also storage and timing channels. Storage channels write to a storage location in some network data, for instance, to the reserved bit in the IP version 4 header or the ICMP payload that we just saw, while timing channels modulate the timing behavior of network traffic to signal hidden information. A simple example is to modulate the inter-packet gaps, so the timing between succeeding packets. For instance, you can send packets with a delay of 1 second or 2 seconds to indicate a 0 or a 1 bit. There are also noisy and noise-free channels. Noisy channels are those that, well, are not noise-free, and noise is a disturbance in that sense, and usually randomized, at least in many cases. So for instance, if you use a network timing channel that modulates the timings between succeeding packets, and you use the timings of 0.001 and 0.002 seconds or something like that, then other network traffic might influence the timings, because hops in between might be busy with processing other packets, so your own packets might be delayed, and then you have noise. It's always nice for the Covert channel user to have a noise-free channel, but in many cases that's just not possible. So these are the very fundamental categorizations. Now I will go into some network-specific, more sophisticated differentiation. So there are, first of all, actually it's not network-specific in any case. So active and passive covert channels, for instance, are not network-specific, but here they play a big role. So an active covert channel is one where someone actively sends traffic. So the covert channel sender, which I abbreviated with CS, and the covert channel receiver, which I abbreviated with CR. So the covert channel sender generates its own traffic to hide information in this traffic. The over traffic should appear as legitimate traffic, but the truth is there's some hidden traffic inside it. And so the passive way would be to piggyback traffic generated by a legitimate user, basically as a man in the middle, that can be on the host of the legitimate user or in between. So it can be integrated in the TCP IP stack of the sender, like done by Joanna Rutkowska during some CCC talk several years ago, but it can also be done on a hop in between. And so the traffic passes by, and the covert channel sender modifies the traffic, but does not generate own traffic. And the covert receiver would read the message also here from the traffic. However, the receiver is less important for the active and passive part, as long as the receiver can read the traffic. It does not matter so much. So the main differentiation is between the sender, the active and passive sender. There are also reversibility methods where the passive receiver would restore the original traffic. And that's a capability that is specific to passive covert channels. So the covert receiver would try to restore the original traffic and then forward it to the legitimate destination, so that the legitimate destination does not see the original, the covert channel content anymore. For instance, if the covert sender would modify the reserved IP bit, IP reserved bit, then whatever message the covert channel receiver receives, it could always clear the reserved bit, so that the legitimate destination always gets a 0 bit. The intentional versus unintentional or side channel is So the side channels are a subtype of covert channels. They are covert channels that send without having the intention to send information. There's interesting work by Sebastian Schinzel from a few years ago, and I linked his talk here. I just want to show some central idea here. So instead of having a covert sender, we have a side channel sender here, or a target, an unintentional sender, and a covert receiver that measures something, some timing information, for instance. And so it could work as follows. Let's say the target reacts differently to depending on which information the covert receiver sends to the packet to receive the actual information. If the covert receiver is a web client and this is a database or a wiki, then the covert receiver could send lots of login credentials many times and measure how long it takes for the reply to arrive. And when the reply arrives, the time delta is computed. And the thing here is, let's say there's a SQL database, an SQL database at the target, and let's assume there's a credential sent by the covert receiver that contains an invalid username. So the target would say, okay, the username does not exist, and some error message would be returned. But if the username exists, and also a password would be sent in the same packet, then also the password would need to be checked, and maybe some additional permission. So the target system needs to perform more actions, or in other words, needs to invest more CPU time. And then the reply will take slightly longer. So delta T will be higher, and the covert receiver can try to measure this. So this is an unintentional information sending process going on here, and that can be exploited to determine, for instance, which usernames exist and which do not exist. Another type of covert channel differentiation is between direct and indirect covert channels. In a direct way, the sender directly sends to the receiver, but in the indirect way, some intermediate node is exploited to signal hidden information. For instance, let us assume this is a web server, the IN is a web server, and the covert sender sends lots of traffic to the web server or none. So over time it sends lots or not so much, more, little, and then a lot of traffic for some longer time. And let's say that this is a signal that can be understood as 1010111101 or something like that. The idea here is to influence the load on the web server, and while the covert receiver tries to probe and tries to also get requests fulfilled from the web server, the response time of the web server will take longer if the covert receiver requests a website during a high load from the covert sender, and it will take less time if the covert receiver requests a website while there is little or no load from the covert sender. So this way we have again a side channel that is exploited here, but intentionally, and so it's not as intentionally influenced by the sender, although this is an unintentional sending process here from the web server. And it's an indirect one because the intermediate node is like a proxy or a cache for the information. I will, in a few chapters, deepen the knowledge of you in the sense that I will speak about such network caches. We published work also on network protocol exploitation to store data in network protocol caches, and I will also speak about reversible data hiding methods, at least about those that are already published, and about many more details of sophisticated hiding methods. But first, we need to understand more about how data can be hidden. So which hiding methods do actually exist? These are more models and general differentiations between types of covert channels, but in the next chapter, we will learn what hiding methods do actually exist. Because so far we saw very little, only the reserved bit exploitation and the ICMP payload exploitation. But these are very simple methods and there are many more.